In this video, we're going to solve one example of how to determine the critical points of the function x plus y plus 1 over xy, where x and y are positive. And we're going to look for the global minimum and global maximum as well. So I'm going to start the solution by finding the first derivative with respect to x. Let me rewrite this part of the function as xy to the power of -1. Now, when I take derivative with respect to x, I get 1, 0, and then I'm going to use chain rule in here. So 1 minus xy to the power of -2, derivative of the inside function with respect to x is just y. So I can rewrite this as 1 minus y over x squared, y squared, and if I simplify that, I get this. Okay, and then I'm gonna find partial derivative with respect to y. We're gonna do the same thing. Just because the function is symmetric with respect to x and y, I just replace any x with y and any y with x. So I get 1 over y squared x. And I'm gonna set both of them equals to 0, so I have a system of equation to solve. For the first one, I'm gonna bring the fraction on the other side, and I'm gonna do the cross multiplication like this. And so I get x squared y equals to 1, meaning that y can be 1 over x squared. Now I'm gonna plug in y equals to 1 over x squared into the second equation. So y equals 1 over x squared. So I get what? I get 1 over, instead of y, I have 1 over x squared times x, which would be 1 over x cubed, and therefore 1 from here is equal to x cubed from here, and so x is equal to 1. So x is equal to 1, and I'm gonna plug it into here. I get y equals to 1. So the critical point, is 1, 1. Let's see if the critical point is maximum or minimum or saddle. So I'm gonna find the d. D is fxx, fxy, fyx, fyy. That's why I need to calculate all these three. So I'm gonna do fxx. So this is, actually let me simplify this part. This is fx. I can write fx as 1 minus x squared y to the power of -1. And so fxx would be, 1 goes down, it would be x squared y to the power of -2. Derivative of inside with respect to x is just 2xy. I'm gonna find fx with respect to y. It would be x squared y to the power of -2. Derivative of inside with respect to y, it's just x squared. Now we're gonna do the same thing for fy. Fy is 1 minus y squared x to the power of -1. So I'm gonna take derivative of that with respect to x. Okay, so it would be x y squared to the power of -2 times derivative of inside with respect to x, just y squared. And then I'm gonna take derivative of that with respect to y. So it would be y squared x to the power of -2. Derivative with respect to y is 2xy. Okay, I'm not gonna be worried too much to simplify that. It's just because I'm gonna plug in 1, 1 into this. So d at 1, 1, it's what? It's gonna be 1 to the power of negative 2, which would be 1. 2 times 1, 1 is just 2. And then I get a 1 to the power of negative 2, which would be 1, and then 1 squared. And then the same thing, 1 to the power of negative 2, and then times 1 squared, and then 1 to the power of negative 2 times 2 times 1, 1. So I get a 2. So I get 4 minus 1, which is 3. So d is positive, which means that I need to take a look at fxx at 1, 1. fxx is this function in here. At 1, 1, it's just 2, which is positive. Therefore, the point 1, 1 is a local mean. Okay, let's look at the graph of the function. Okay, this is the function z equals to x plus y plus 1 over xy. This is the graph of the function, and the part that we are looking for would be on the first octant. It's just because we are looking at where x is positive, y is positive. So basically just this part of the function we need to look at. Okay, as you see, this part we just have one local mean, which would be also the local max, which would be also the global mean. The local mean is also global mean for this function when x and y are positive. And then for finding the global max, we need to look at the boundary, or at the infinity. The boundary of the domain where x is positive and y is positive would be the x-axis and y-axis. And as you see, the function goes to infinity as these boundaries. Okay, it goes to infinity. Let me see. Yeah, maybe you can see it better in that case. We are just looking at this part of the function where x and y are positive. And so the function does not have any global max, as you see here. Just have one local mean, which would be the global mean, but not local max. So let me write this. So the point 1, 1 is also global mean of f on the domain D where x and y are positive. Okay, but where is the local, but where is the global max? It must be along the boundary of the domain, or at infinity. So for the boundary of the domain is x positive and y positive. So we're gonna take x goes to 0 for the y-axis, and then y goes to 0 to go to look at the x-axis. So let me write the function. The function is like that. As you see, when x goes to 0, this would be 0, but we get infinity, 1 over 0, we get infinity. And when y goes to 0, this would be 0, and then again we get 1 over infinity, which means that in both cases, f goes to infinity. So no maximum in here. How about at infinity? At infinity, when x goes to infinity, or y goes to infinity, the fraction would be 0, but again we get infinity in here or infinity in here, which means that when x goes to infinity and y goes to infinity, also the function goes to infinity, which means that there is no global maximum.